So here we are now going to look at sidewise and the horizontal displacement of light rays. That is what we are now going to look at in this episode here. So what is the sidewise or a horizontal displacement of light rays? What is very true is that when a ray of light is incident from one medium to another, it changes direction and it's displaced sidewise. This is called the lateral displacement. Okay? That when we have rays of light that is moving from one medium to another, it will always change direction to be refracted. And whenever they are refracted, there is some kind of displacement, isn't it? That it goes through. That is what we are calling lateral or sidewise displacement. And then I can say, consider a ray of light incident on a glass prism of thickness T, refractive index N, and emerges from it into air with a sidewise displacement D. Okay? And the diagram for our statement, I would say that if we are considering a glass block like this, let me exaggerate it. If it is incident, point O, and now it is refracted here, and now moves out in air. If this is the thickness, we are calling it T, and refractive index that. If this is angle I, this will be angle R, isn't it? So we are saying that this light ray, in reality, when it was coming toward this block, it was moving in this direction. But now you'll bear with me, or you'll realize that this light now, as it's moving out, okay? It came in this direction, it bent and now moved out from here. That means that it has been displaced aside, downward. And this is what we are calling the D. That initially it was in this line, but you'll see that if it becomes refracted, moves out, the two will be parallel. Isn't it? But realize that it is no longer in this line, but now it is going to move in this. So it has been displaced from its line to another one. And this is what we call sidewise displacement D. Now, the question is, how do we get the expression for this sidewise displacement D? That is still my D. I can say from our triangle AOB, from that triangle of ours, I can say cos r is adjacent over hypotenuse, and I can say cos r is the adjacent is t out of OB, and that means my OB can be equal to the thickness, okay? OB can be the thickness divided by cos of r. That is my O. And I can say from also my triangle, if I put here D, from my triangle BOD, okay? Don't forget this angle here can be now I, and that means this is I minus R. From that triangle, I'll now say this angle here, from here up to here. This one is the same as I minus R, because this one, if this is I, even all of this is I. But if this is R, that means this is I minus R, this one here. Okay, so from that triangle, I can say what is the sign? What is the sign of I minus R? Sign of I minus R, okay, is equaling to the opposite, that is D, over hypotenuse OB. So that means that my D is equaling to OB sine of I minus R. And then from there I'll say, I can now say I know OB as that. That means my D can be equivalent to T out of cos R times sine I minus R. So displacement can be equaling to T, you can call that and say R times the sine of I minus R. So that is if you are to get the sidewise displacement. We said sidewise displacement is from here up to this point here. How far the ray has shifted its direction. That initially it was moving here, but as it's emerging out now here, what is this D? So we started by looking at this simple triangle here. The angle of refraction was that, and the cos was giving us adjacent, which is OA over hypotenuse OB. But adjacent, we realize is our T out of OB. And we say the OB, when we bring this one here, that will come here. That. And then from this triangle here, we say if the whole of this angle is I, this angle will be I minus R. And then we looked at sine of this angle here. It was opposite, which is the D, okay? D out of hypotenuse, which was OB. But I already looked at OB behind there. So it is opposite hypotenuse. And then we say D can be equal to OB sine of this. But OB behind there, we say is equivalent to T out of cos R times that. So this is sidewise displacement. But what about horizontal displacement? Horizontal displacement is the AB. That initially it entered from here, but it came out from here. So that means that what is this distance here? AB is the horizontal displacement. So therefore, from there I can say, from my triangle AOB, what is my tan of R tan R, tan is opposite adjacent, which is AB, toward opposite adjacent, AB out of OA, and that is same as AB out of T, and my AB is T tan R. So if they ask you to calculate the sidewise displacement, it will be equivalent to AB tan over R. Please, they will even one time ask you to distinguish between horizontal displacement, distinguish between lateral and horizontal displacement. So you can now get your idea of defining horizontal displacement by maybe saying horizontal displacement is the distance between the normal and the point of emergence of the light rays moving from one medium to another. Because now, if we talk about that, our normal is this. So the distance from here at the point of emergence, isn't it? The normal at the point of the normal on this lower part and where it is emerging from is what we are calling it the horizontal displacement. And then also you can talk about sidewise displacement. Okay, so you can get how now to define that one as the sidewise, the distance between the initial and the final direction of the light rays. That initially it was moving in this direction, but finally it is that. So the distance between the initial and the final is what we are calling lateral displacement. Let's meet now in some example involving this.